Hey guys, and welcome to JP Academia. In this video lecture, I'm going to discuss motion in one dimension. And we have the following topics. First, we will define kinematics, followed by distance and displacement, average velocity and instantaneous velocity, average acceleration and instantaneous acceleration, constant acceleration equations, which is very important. Then the last is freely falling bodies. It was not until the 16th and 17th centuries that our modern understanding of motion was established. Mechanics is actually the study of the motion of objects and related concepts of force and energy, while kinematics refers to the description of how objects move. Now let's start by defining displacement and distance. Displacement in physics refers to the change in position of the object. So this quantity has both magnitude and direction. Thus, it is a vector quantity. On the other hand, distance is a scalar quantity. Thus, it has a magnitude only. Let us have an example here. Let us say Peter, a certain person Peter, walks from the origin. So we have here 80 meters east as shown in blue. Then Peter walks 30 meters west this time, the one in orange. The total distance traveled here, therefore, is 100 meters, while the displacement, taking into account the direction, is 60 meters. Therefore, displacement may not be equal to the total distance traveled in this case. If the object is at position, let's say, x sub 1, this one, at time t1, and at x sub 2 at time t2, then the change in x is equal to x2 minus x1. Okay, so next we have speed and velocity. Let's start with speed. Speed refers to how far a certain object travels in a given time interval, regardless of direction. Average speed, as shown here, of a certain object refers to the total distance traveled divided by the time elapsed to travel this distance. On the other hand, we have here velocity that takes into account both the magnitude and direction of a moving object. And the average velocity can be expressed as the displacement, delta x, over the time elapsed, delta t. Note that the average speed is not necessarily equal to the magnitude of the velocity. So we have here the mathematical expression for the average velocity. If the average velocity is evaluated for a time interval that approaches 0, then we have an instantaneous velocity. This looks familiar if you have taken your basic calculus. Instantaneous velocity is the limit of the displacement delta x over delta t as delta t approaches 0. We make the time elapsed approaches 0 until we get the velocity at that given instant in time. So that's why we call this one instantaneous velocity. The velocity is just the slope of the graph of x versus time, as illustrated here in my drawing at the right. When the slope is positive, the object is moving to the right based on our sign convention. When the slope is negative, here, shown here, the object is moving to the left. While when the slope is 0, the object is stopped. The rate at which velocity is changing is measured by acceleration. The average acceleration can be calculated based on the velocity v1 at time t1 and velocity v2 at time t2, and it has a unit of meters per second, while the instantaneous acceleration is expressed as the limit of change of velocity over the change in time as delta t approaches 0. We can therefore express this one in terms of derivative. So we have here the first derivative of the velocity v with respect to time. In addition to this, the acceleration is just the second derivative of the displacement with respect to time. Now let's do a graphical analysis for displacement, velocity, and acceleration versus time. Let's start with this one. So at this portion, we can say that the object is moving at the positive x direction. While for this one, given that we have a constant x, therefore we can say that the object stopped. For the second graph, we have here, so at this portion, the object is traveling with increasing speed. While for this flat region, the object has a constant speed, while for this one, the object is traveling or has a decreasing speed. Last, we have this graph, and we can say that at this portion, we have a positive acceleration. Then for that is increasing. Then for this one, we have a decreasing acceleration, which is still positive. Then we have here zero, or we have here a constant acceleration. One way to simplify our analysis of motion is to assume a constant acceleration. In this case, we can obtain useful expressions for velocity and acceleration by integrating this acceleration expression. So we have here a is equal to the first derivative of velocity with respect to time. And this is constant. So we get v here by doing some integration. So we integrate this one, a times dt, and this is just a simple integral. So this is equal to at plus a certain constant c1 or c sub 1. And we can get this constant c1 at t is equal to 0. So c1 is equal to v naught, which is the initial velocity. So now we can rewrite this one. So v is equal to at plus v naught. And this is our first expression for the velocity. Now we have this one. So we know that velocity is just the first derivative of your displacement x with respect to time. So given this integration, so using the same method as we have shown earlier, so we integrate this one v dt, and this is equal to this quantity here. So at plus v naught, so which is this expression for our velocity v, and therefore we can write your displacement x as this, or 1/2 at squared plus v naught t plus c sub 2, which is just a constant. So we can get that constant at t is equal to 0. So c2 is your initial displacement x naught, which is sometimes we assume 0. And therefore, we have this two expressions for constant acceleration. We can get a useful expression for velocity related to its displacement. So using equation 1 to solve for time t, we have the following. So v is equal to at plus v naught, and this is our expression earlier. So t is equal to v minus v naught over a. This now we can substitute this one to our equation 2 that we have shown earlier. So we have this expression, and let us assume that x naught is equal to 0, or the origin. And therefore, doing some algebra manipulation, we now have this final expression. So the final velocity is this one. So v squared is equal to v naught squared plus 2ax. This constant acceleration formula is useful if time is not given, but we have information for the displacement. Now we consider objects moving upward or downward along a vertical axis, neglecting air friction, and we only consider the influence of gravity here on a certain object. We will assume for this case a constant acceleration due to the force of gravity g with a magnitude of 9.80 meters per second squared. Note that this acceleration is downward, hence negative, whether the object is falling downward, moving upward, or momentarily stop at the highest point. And that ends my lecture for this video. Hi! If you have learned something in this video and you like my content, please consider subscribing my YouTube channel, GT Academia. See you in the next video.